The Gripen E operates with a new agile architecture system, which allows the aircraft to be upgraded with new tactics and new capabilities seamlessly.
What we designed the system for is actually to be able to withstand the extreme max in terms of cold, so minus 40, minus 45.
10,000 research and manufacturing jobs could land in Canada if Ottawa adds the Swedish fighter jet to its military fleet.
We, as Saab, we are prepared to do that technology transfer to Canada and support that build-up.
The lights never turn off at the Rolls-Royce test complex in Derby. But on that particular Tuesday at 3 in the morning, the atmosphere carried a different weight. Because inside a climate chamber built to recreate the most punishing environments on Earth, engineers were preparing to validate a propulsion system that could quietly redraw the balance of power in the Arctic. And the data recorded over the next few hours would circulate far beyond the walls of that facility, moving through defense ministries, intelligence channels, and Air Force headquarters across Europe and North America, leaving behind a realization that something fundamental had shifted in cold weather air combat. The chamber temperature sat at minus 52 degrees Celsius, simulating an altitude of 40,000 feet, with Arctic wind chill replicated. Through controlled airflow systems that cost more to install than many frontline fighter aircraft. And mounted on the test stand was a new generation turbofan, carrying documentation marked for the Royal Canadian Air Force, wired with hundreds of sensors tracking combustion stability, lubricant viscosity, fuel atomization, thermal expansion rates, and structural stress tolerances across a brutal temperature spread. As technicians completed final checks, knowing that the objective was not incremental improvement, but proof of reliability, where most engines struggled to function at all. When the sequence began, the engine ignited from a fully cold-soaked state without preheating systems or auxiliary ground equipment, accelerating from inert metal to stable combat thrust in 93 seconds despite the extreme cold, a figure that would later become the most discussed number in closed-door briefings from Ottawa to Stockholm, because comparable American alternatives under similar minus 45-degree testing conditions required an average of 14 minutes to achieve operational readiness, often experiencing thrust degradation of roughly 30% during initial operation while critical systems stabilized. That difference was not cosmetic, and it was not theoretical, because the test series ran for more than 400 cumulative hours in extreme environment trials, documenting repeatable cold starts, sustained thrust output, and structural durability under rapid temperature transitions, and once portions of those results leaked into defense circles, the reaction was less public outrage and more stunned recalibration, as intelligence agencies quietly confirmed that the capability gap between this Canadian configured platform and its nearest competitor represented the largest Arctic performance disparity recorded in modern fighter aviation. Understanding why that matters requires stepping back from the chamber and examining what the engine represents industrially, because Rolls-Royce did not embark on this development program solely to fulfill a single contract, but rather to address a long-standing limitation in conventional turbofan design that prioritized high-temperature cruise efficiency while accepting compromises in extreme cold performance. A trade-off that made sense for most air forces, but never aligned with Canada's operational reality, where sovereignty patrols over the Arctic archipelago demand aircraft that can launch reliably in conditions that ground others. The breakthrough begins with lubricant chemistry, an area rarely discussed outside engineering conferences, yet decisive in sub-zero operations, because traditional aviation lubricants thicken dramatically as temperatures plunge, increasing friction, delaying spool-up times, and placing enormous strain on starter systems, whereas the new formulation developed for this engine maintains stable viscosity down to minus 60 degrees Celsius, allowing internal components to rotate freely without external heating, reducing wear, lowering energy demand during ignition, and eliminating one of the primary causes of cold start delays in existing platforms. Fuel behavior posed another challenge, since jet fuel at extreme cold forms wax crystals that restrict flow and compromise atomization, forcing many designs to rely on preheating mechanisms that add complexity, weight, and maintenance demands, Yet engineers address this by redesigning the injection system to optimize spray patterns and droplet size at low temperatures, preventing crystal accumulation without energy-intensive heating cycles, resulting in a lighter, simpler architecture that performs consistently across a broader thermal envelope while reducing potential failure points in forward-deployed Arctic bases. Material science advances underpin the entire system, because conventional turbine alloys are optimized for sustained high-temperature resilience, but are vulnerable to microfractures when exposed to sudden thermal shock after prolonged cold soaking, a scenario common in Arctic operations where aircraft sit in sub-zero conditions before rapid engine ignition. And to counter this vulnerability, metallurgists formulated a new alloy composition capable of tolerating temperature swings from -50 to +900 degrees Celsius without structural degradation, creating durability benefits that extend beyond aviation into energy production and industrial turbine applications. Each of these innovations would have been significant individually, yet their integration compounds performance gains in a way that transforms operational timelines, because rapid ignition enabled by stable lubricants feeds directly into efficient combustion, supported by optimized fuel atomization, while shock-resistant alloys preserve reliability over repeated cycles, producing an engine that not only starts faster, but sustains rated thrust immediately, eliminating the prolonged warm-up windows that can expose aircraft and crews to tactical vulnerability. Consider an Arctic alert scenario in which long-range radar detects unidentified aircraft approaching Canadian airspace, and contrast two response timelines, one in which engines require more than 10 minutes to stabilize before takeoff, and another in which 93 seconds suffice to generate full thrust. Because in northern engagements, measured in minutes rather than hours, that gap determines who gains altitude advantage, who locks targeting systems first, and who dictates the geometry of interception, especially when paired with long-range air-to-air munitions, such as the Meteor missile already integrated on certain European platforms. Parallel testing conducted under identical environmental controls included evaluation of the Lockheed Martin F-35, equipped with the F-135 engine, and while the aircraft remains formidable across many mission profiles, documented cold start averages of 14 minutes at -45 degrees, coupled with temporary thrust reduction during initial operation and reliance on specialized maintenance tools not readily available at improvised Arctic strips, underscored a distinct disadvantage in the northern theater, a conclusion reflected in internal assessments even as public statements emphasize broader performance envelopes. Integration speed further amplified the breakthrough because the Swedish manufacturer Saab had designed the Gripens airframe with modular architecture intended for future engine evolution, allowing the updated power plant to be incorporated into Canadian production lines with minimal structural modification, requiring approximately 6 weeks to revise assembly procedures and roughly 90 days to qualify the revised aircraft configuration, a timeline that contrasts sharply with the multi-year certification cycles associated with deeply integrated platforms optimized around a single engine specification. This design philosophy favors adaptability over rigid optimization, ensuring that technological advances can be folded into the fleet progressively rather than waiting for wholesale generational replacement. And for Canada, whose operational theater presents unique climatic demands, that flexibility translates into a procurement model aligned with national priorities rather than inherited constraints from foreign supply chains focused on different environmental assumptions. Arctic sovereignty is not an abstract political slogan, but a logistical reality defined by persistent patrols over the Northwest Passage, remote forward operating locations, and winter temperatures that regularly plunge into ranges where many Allied aircraft face degraded readiness, and by fielding an engine validated across 400 hours of extreme trials. The Royal Canadian Air Force secures year-round operational certainty instead of seasonal capability, eliminating the assumption that winter conditions create predictable surveillance gaps exploitable by foreign vessels or probing aircraft. Training evolution follows naturally, since pilots operating from austere Arctic strips in live conditions gain experience that simulators cannot fully replicate. Mastering rapid cold starts, thermal transition management, and navigation in magnetic anomaly zones, thereby cultivating an institutional knowledge base that positions Canada as the leading Arctic air warfare authority within NATO, with the potential to host specialized courses that attract allied aviators seeking exposure to real-world polar operations. The export implications are equally significant, because cold climate nations evaluate procurement decisions through the lens of reliability in sub-zero environments, and with Norway, Finland, and Sweden maintaining northern defense responsibilities, while other countries such as Kazakhstan and Mongolia assess requirements along vast cold borders, the appeal of a platform whose engine has demonstrated verified -52-degree performance becomes self-evident, particularly when intellectual property protections secure long-term revenue streams for Rolls-Royce through licensing, royalties, and derivative industrial applications. Financially, the program's impact extends well beyond the initial Canadian contract, as patented alloy compositions, advanced fuel injection systems, and proprietary lubricant formulations create diversified income channels across aerospace, energy, and heavy industry sectors, reinforcing Britain's aerospace manufacturing base while illustrating how targeted innovation can erode entrenched market dominance previously sustained by limited competition. Within the United States, official reactions acknowledged impressive cold weather capability while reaffirming overall platform superiority, a carefully balanced formulation that avoided direct claims of Arctic advantage, and separate intelligence analyses reportedly characterized the breakthrough as a generational advance in cold weather propulsion technology, noting that similar research pathways had not been aggressively pursued domestically, in part because procurement structures did not prioritize that niche environment. European aerospace research agencies responded swiftly, launching parallel studies into cold weather propulsion improvements, stimulated by proof that long-standing assumptions about performance ceilings in extreme climates were no longer valid, thereby reigniting competitive dynamics within the alliance that had been muted during periods of limited supplier diversity. Across defense planning documents, a broader lesson emerges concerning sovereignty and capability alignment, because procurement strategies anchored in monopoly supply chains tend to reflect the strategic priorities of the supplier nation, whereas diversified partnerships allow countries to tailor engineering solutions to their own operational landscapes, and in Canada's case, collaboration with British and Swedish industry produced a propulsion system optimized explicitly for Arctic excellence, rather than adapted as an afterthought. The test data circulating from that Darby chamber confirmed measurable performance metrics rather than marketing claims, reinforcing conclusions reached during European evaluations and validated through live exercises in northern conditions. And as incremental upgrades continue along the development pipeline, including 17 identified performance parameters slated for phased improvement over the next 36 months, the fleet rolling off Canadian assembly lines in Ontario will evolve continuously, integrating fuel efficiency gains and advanced thermal management refinements without disrupting pilot training or maintenance ecosystems. This iterative approach contrasts with procurement models that prioritize configuration stability over adaptability, and by blending limited American interoperability assets with a continuously evolving European-sourced fleet, Canada positions itself to benefit from both standardized alliance integration and rapid innovation cycles tailored to national needs, ensuring that Arctic readiness remains not a temporary edge, but a sustained strategic advantage. Moreover, strategic wisdom means recognizing that different missions demand different tools rather than forcing one platform to cover every scenario, whether it fits or not. And in Canada's case, that clarity reshaped the way air power is built, trained, and sustained in the Arctic, where geography and temperature dictate terms that no briefing slide can soften. When pilots operate the most Arctic-capable fighter platform on Earth inside Canada's own northern theater, they develop a level of experience that no other air force can replicate, because skill forged in real sub-zero launches remote strip recoveries, and shifting polar weather patterns goes far beyond technical manuals and simulator hours. That human expertise becomes a strategic asset in its own right, extending well past the lifespan of any single aircraft. As those aviators rotate into instructor roles, staff positions, or eventually civilian careers, the knowledge accumulated through real Arctic operations feeds directly into training syllabi, doctrine updates, and long-term capability planning. Retired pilots move into defense contractors, research institutions, and advisory boards, carrying hard-earned operational lessons into the next generation of systems. In that way, human capital compounds alongside technological capital, creating a durable advantage that cannot be measured only by thrust ratings or cold start times. The same dynamic unfolds on the engineering side through the close partnership between Canada and Sweden. Personnel from Saab working inside Canadian facilities collaborate daily with local technicians and pilots, solving integration challenges face-to-face rather than through distant contract negotiations. When a Swedish engineer develops an idea to improve cold weather resilience, the conversation begins immediately with a Canadian counterpart who understands the operational stakes. When a Canadian pilot identifies a tactical limitation during winter exercises, that feedback reaches designers without waiting for layers of procurement bureaucracy to filter the message. The speed of that exchange becomes its own competitive advantage, because innovation thrives when communication flows directly between those who design and those who fly. The Atlantic Production Partnership strengthens that loop even further. Swedish engineering teams operate in Ontario, British propulsion specialists contribute from Montreal, and Canadian aerospace workers absorb expertise from both, creating a continuous two-way exchange of insight. Arctic operational data flows back to European designers, who refine systems based on real-world performance rather than abstract modeling. That feedback cycle is precisely what allowed the cold weather propulsion breakthrough to emerge in the first place. Canadian requirements were treated as serious engineering challenges rather than niche add-ons, and the designers at Rolls-Royce who solved them advanced within their organization for doing so, reinforcing an institutional culture that rewards meeting allied operational needs. In contrast, a monopoly environment rarely encourages that level of specialization. When one supplier dominates, the incentive to tailor solutions for unique climates weakens, especially if the core customer operates in different conditions. The engine now validated in extreme cold exists because engineers were motivated to address a defined Arctic requirement, and because the partnership structure ensured those requirements carried weight inside the design process. The political sustainability of this advantage also shapes its long-term impact. In theory, the United States could invest heavily and develop a competing cold weather propulsion system, but historical procurement cycles from initial requirement to operational deployment often span 12 to 15 years. The current European engine already holds a substantial operational lead, and development does not pause after entry into service. Continuous upgrades are underway, informed by live Canadian experience in sub-zero conditions. By the time a hypothetical competitor reaches equivalent cold start performance, the benchmark will have moved forward again. That trajectory matters more than any single data point. Today's 93-second cold start could become 60 seconds within 5 years as refinements accumulate, then perhaps even faster as materials and software evolve. If another manufacturer begins development now aiming to match 93 seconds a decade from today, the strategic context will have shifted so far that parity at an outdated benchmark offers little practical value. Observers in France and Germany recognized that reality during their evaluations, understanding that they were endorsing a development path accelerating faster than alternatives, not merely approving a snapshot of current capability. Across the broader transformation of NATO procurement patterns, the shift from reliance on a single dominant supplier toward diversified European partnerships has reshaped incentives around innovation. Competition revived research intensity. British engineers pursued cold weather solutions that had long been sidelined. Swedish design philosophy emphasized modularity and continuous improvement, ensuring that new advances could be integrated without rebuilding entire fleets. Canadian operational urgency provided the real-world testing ground that turned theory into validated performance. All of those strands converge in a single image, an engine mounted in a climate chamber in Derby at 3 in the morning, temperature locked at minus 52 degrees Celsius, igniting from a fully cold-soaked state and reaching stable thrust in 93 seconds. That moment symbolizes more than a technical milestone. It reflects a sovereignty-driven strategy that aligned industrial incentives with national requirements, encouraged collaboration instead of dependency, and produced capabilities tailored to the harshest operational environment on the planet. After examining the hardware, the strategy behind it, the economic stakes, and the alliance politics surrounding it, everything ultimately circles back to that freezing chamber and the moment the engine came to life under conditions most aircraft are never built to face. Canadian pilots now fly with an Arctic advantage shaped by advanced engineering and sharpened by real operational experience. So, what does that mean going forward? Does this mark the beginning of a long-term shift in Arctic air power? Can competitors realistically close the gap, or has the trajectory already moved too far ahead? And how will this influence future NATO procurement decisions in regions where climate is not a footnote, but the defining factor? Share thoughts in the comments because informed debate matters when the stakes involve national defense and alliance balance. Make sure to subscribe and turn on notifications so future deep dives do not get missed. See you in the next one.